Alright, time for another DraftScience video presentation. Unfortunately, I just made a really good video, and but I didn't fix the settings. I had composed a little video to make, and I changed the settings on the screen recorder, and so a perfectly good video ruined. But anyway, so now I have to do it again. And so I thought I would just play some of the old video, just because I started with subjects that are kind of important, and I just don't know how to reduplicate that. And it's just irritating, because it was good. Alright, time for the DraftScience video presentation. So, on the subject of kinetic energy versus momentum, I'm making a simple kind of argument that this is like a wave-particle duality thing. You can even go to the idea that gravity is an actual force versus people who think it's some sort of mathematical concept. It doesn't have anything to do with a force. Anyway, yeah, you have to choose, and you have to choose wisely. And frankly, conventional physics is, in all of these questions, chosen unwisely, is the argument. And so, yes, so the wave-particle duality thing, wrong choice, waves. Force versus, I don't know, mathematical construct. No, force is really important. The speed of light versus the speed of force. What do we name it? Okay, yeah, the sensible thing is it's the speed of force, because all the forces move the same speed. Lots of bad choices. Plus and minus they got wrong, right? No, lots of bad choices. You can see it because of the lack of logical continuity. It doesn't add up. So if you do add up the pieces, you can figure out which one's the right answer, would be my argument. The evidence does have elements to it. It can't all be consistently aligned in one camp and work. It can only work in one place. I can argue that momentum always works. You can be fooled sometimes. It can be things that are a little tricky, but it always works. And particles always work as a theory because particles can easily look like waves. Waves can't look like a particle. Right, so now I'd say the evidence just indicates all of this also. So the only thing where you're really saying is waves are always an abstraction of group behavior. They're never an actual one wave. You never follow one wave in any of these things as experiments. It always requires the participation of many of the events and all of that stuff. And so it's clear that, yes, particles can look like waves in group behavior. But we always know you're sitting at the ocean and some water hits you, okay? They're individual water molecules. They're not waving. They're individually moving with velocities and momentum in directions. And it's those kind of things that give it away, okay? The truth. So there's been a lot of conversation about things as simple as just springs and devices for storing energy. So I would say that a bit of insight I could offer you, something that might make the world more understandable to you, is to see a thing like a spring or a lever, okay, a balance. So I redraw those. Okay, so so the idea is that these are important devices and they're understood. This one's understood as a storage device, and this one's understood as a measuring device. Okay, the balance. But they have another feature about them. They're more than that. In terms of understanding, they're a conversion device. Okay, they take MV, any NV going in, any ratio of mass to velocity can go in, and you will convert it on the other side to its reciprocal through the process of the balance. If you move one side of the lever, it moves this bit slow. It moves this bit fast. So you can change the velocity or the mass, or the relative mass, the abstract mass of an object by merely moving it on the balance. You can make something light look heavy from this perspective merely by putting it further out on the balance. Traditional looking thing there. As not just storage devices. That is not just that you can create a circumstance where you apply energy and they can hold the energy through a simple mechanism. Okay, like just, the balance it has to be active. It's not a storage device. This is a storage device. Can be a measuring device. But it also does something else. It can be a conversion device, because all I have to do is put an extension, okay, on this, and I can put a half weight here and balance. And so so that's just saying, okay, I can take half the mass, I can take something half as light, and I can put it out here, and now I can make it look from this perspective like this object, like it has the same mass as, even though it doesn't have the same mass as. But the price you pay for that is a reciprocal change in the velocity that it will move. And that connection always exists, and that will be argued in the Professor Lewin video clips that I'm going to play. Change the MV relationship that something has. I can keep the same momentum, but I can change, okay, one of these numbers and make an apparent change in the other. I don't actually change something's mass by moving it, but I will change how it's measured, because I will change its velocity, because I'll change the arc of the swing. And this is a higher V and this is a low V. So it's more than just a measuring device. It's a device where you can apply a change. You can convert your momentum from being heavy and fast to being light and slow. And you can do the same thing with a spring. A spring, whether it's a coil of wire or a bent piece of metal, no matter what form it's in, it takes the energy and it doesn't care. You can come in with lots of velocity and very little mass, or lots of mass, to do it. Right. So this is sort of to the William Sumner way of drawing it. But I mean, yes, a spring allows you to put a big mass in and a little velocity, and get a big velocity out and a little mass. This is the conversion that it allows you to do. So, and this also allows you to do the same kind of conversion, is to fool things, okay, and cause reciprocal changes in mass-velocity relationships. But it's always got to conserve the momentum. The spring can't make momentum, and it can't really destroy momentum. Like, what's his face did it? Just make the numbers big. A big velocity and a little mass, or a big mass and a little velocity. And I can put energy in, and this doesn't care how the energy got in. So once I compress the spring, you can give it back in any form. I can take it back like a clock. I can take it back one little tick at a time, one tiny little bits of momentum. Or I can take it back, try to take it back all at once. Now, the limitation is the spring itself can only go so fast, so it has a limit to its velocity. All right, and that's the maximum velocity it can give. And if you're really light, the spring isn't going to give you much, because the spring can't go as fast as you could have gone. So there's rules, limits, but basically they're very nice conversion devices, and that's what they should first be seen as, is that they can convert any speed and momentum in an asteroid hits, and I can use the energy for hundreds of years. Okay, if I make a big enough spring and I catch an asteroid hitting the Earth, I can compress the spring, lock it, and I can take the energy out over 100 years. I can collect the energy that's in the spring, so I can take it out in little tiny pieces. And that's how it should be seen. I think that's helpful to understanding the concept. Now, what's being argued here is that there's this thing called kinetic energy, which distorts this simple view of mass and velocity. So it takes Newton's simplicity and it overtly complicates it. And it does it because of a guy named Leibniz who was really religious, and he wanted the universe to have things called solitons and monads in it, and spirit beings and all that kind of stuff. And so there was this idea that somehow energy, was some special thing, and it wasn't just represented by the simple mv, your mass and times your velocity. That there was this idea that your velocity could was exponential. Was squared, was much more voluminous than it appeared, and so the faster you went, the more energy, the more capacity to compress a spring. So your mass wasn't important to the spring as your velocity. Well, we can kind of know it really doesn't matter. It's the same. They both matter. And that everything that happens to you is really happening. So let's understand first that mass is an idea of the number of atoms you have, the amount of material you're made out of, and it really doesn't have any. So this part I'm talking about mass, as your atoms, and making the argument about gravity, because again, it's really important to understand how forces, real true forces, and fake forces, or forces that we call a force, but it's really a description of what forces are, other forces are causing as an effect, the outcome. And the fact is that gravity, does affect your little bits. It hits everything. So as I will state, when gravity is acting on you, it completely fools your systems, because your systems, you have a little nerve cell that's going to detect motion in these other cells to be triggered. Well, if the whole system is moved, that's what gravity does, it moves the whole system, then the nerves don't feel anything, because nothing changes. But if I push on you, like I punch you in the face, well, then you move the tissues here, and the nerve cell's moving over here, and so obviously there's a disconnect. Now it can sense the change. So you feel okay, these external forces, but you don't feel gravity ever. You never feel the force of gravity. If gravity moved you the speed of light into the sun, you wouldn't feel yourself being pushed into the sun. You wouldn't feel a thing, okay? Because the only thing you can feel, all right, are forces that hit you unevenly, that push on your flesh, or that push on pieces of you, but not all of you. Gravity affects every single little electron, where the other punching force doesn't affect every electron. So you feel the Earth pushing up. You don't feel gravity pushing you down. But the two forces are the same. It's the same amount of punch. You're just receiving it in a different form. One form you can feel, one form you can't. And this is really important to understanding why people get confused and draw wrong conclusions.
To do with motion by itself. It's just saying you have a certain number of bits inside of you stuff, okay? It's just a measure of how much stuff you have. And we use, the idea of mass, we can kind of convert it into this idea that because of gravity, of your mass moving, okay? And that's a weight. But the weight can be, gravity's doing this to you. It's giving you weight by giving you motion, okay? So you weigh 100 pounds. But I could do the same thing. I can turn the Earth and, now you're going this way into the Earth. I just turn, you think of yourself standing here, okay, on the Earth, and gravity's pushing you down. Well, that's just, okay, I put you over here. And so now you get the idea that, oh yeah, now I'm going this way. I'm not going down anymore. And you're getting pushed, though, by the same force. So it's the same thing. If I push something this way, sideways, yes, I'm going to be pushing in gravity, I'm going to fall down, all that kind of stuff. But the point is, it's the same mechanism. 100 pounds this way is the same as 100 pounds down this way. It's just your mass times your velocity. It's just gravity, times your mass. Is your power, your work, your energy, all of those things, your force, your energy, your power, all of that stuff that is just made out of moving your mass. And there's no idea that if you move the mass faster that somehow you can derive more out of it. You can't. It's a certain amount. And gravity doesn't give you more. Nothing gives you more. Any force that doubles, it's, there's certain rules. Now, yes, gravity gives you this illusion because to get the double of your velocity, you have to go 4 times higher than gravity. But that just has to do with the fact that gravity is very different than a pushing force. I mean, just a regular, my hand pushing on some other object. My hand has to just push on one part of you, and it has to be conveyed through the rest of you. Gravity is working on your mass on the elemental level. It's moving the little tiny bits, okay? It's pushing everything. That's why you don't feel it. You don't feel gravity, ever. It's a perfect force in the sense it moves you completely. And so your nerve cells are moving with the sensors. Your sensors are moving with the material they're sensing. So they never detect that they're being moved because they move the piece they're looking at, okay, to be agitated. They can't be agitated because the tissues don't move different than the nerve cell moves. They all move exactly the same in gravity. So you never feel it, ever. You can't feel gravity act on you. You can only feel when you hit something else, it says, I'm going to push you, I'm going to stop the gravity. Now you're going to have to move more mass. And when you have to move more mass, you have to come in contact. And it's the contact that creates this uneven distribution of the velocity. And the uneven distribution means your nerve cells can feel that. They'll see the tissue move away before they did. There won't be an evenness in the movement. That's when you feel it. Okay, so that's why people get fooled. All right, but gravity's doing exactly the same thing, and so it's just how much time you're in gravity. Gravity's like a rain that's falling. It's hitting your little bits, and it's how much.
Okay, so I've made this point before that you're just collecting in a bucket, and how much falls in the bucket depends on how long you're in the gravity, and it's that kind of simple thing. Gravity's just hitting your little bits as if they're buckets. They're collecting the energy in the buckets. More time you're in it, the more you collect, the more buckets you have, the more you collect. That's your momentum, your mass times your velocity. And that's all there is. There's no reason to square anything. It's not logical, it's not reasonable, and there's no evidence defending it. And the other important point was, I can't remember at this exact moment, so I'll continue to play the video.
Time you're in the rain will decide how much rain you collected, how many bits, how many umbrellas you have. You can think of the little bits as umbrellas or inverse buckets, and they're going to collect the rain. So the longer you're in the rain, the more your buckets collect, and that's why there's this relationship with gravity. That's really understandable, but it can fool people, and they think all forces act that way, and all forces don't act that way.
So the point I'll get to is that everything, the amount of energy is just your velocity and your mass, and it can be in any direction. So when gravity gives your mass velocity, it's a weight. When you push on something, it's mass and velocity. It's motion. It's weight. So the whole thing is just really about how much weight your mass has And weight is just a way of recognizing what mass does when it has velocity. Mass has weight when it has velocity. You don't have weight, okay, just sitting in space. You have weight, okay, when you have a relationship to a force, and a force is pushing you. That's giving you weight, and the force is giving you momentum, because the force has it to give.
Actually, no forces really act that way, except things like magnetism, other very invisible forces. But that's, even light doesn't work that way, because light doesn't hit you evenly, and you don't collect it evenly. The back of your head isn't going to collect the light hitting the front of your face, or your eyeballs. All right. So, I mean, some of this perspective stuff, the underlying perspective is really important to having a conversation.
I guess I should just draw a quick picture. I mean, there's just a huge difference between you being deformed, okay, misshapen by something hitting your surface and affecting you, and you being pushed by a perfect wind that blows every bit of you at the same speed. That's the difference. It's the sail, versus just a perfect motion. Gravity's it moves you perfectly, so you never know it did it.
That could be rational, because if you believe a bunch of things that aren't true about how the things work, then you just keep arguing for something else. But I'm just saying it's pretty clear that, so the modern formula is this, okay? The Newton's formula was this, okay? MV is the force, is energy, is your ability to work. All of that stuff is MV. All that matters is how much mass is it and how fast is it going. That's all you've got. And this is the opposing theory, all right? I would argue there's no evidence for the theory, and it breaks all of the continuity of understanding the spring and understanding the lever. The lever are MV devices. These are momentum devices. They really don't obey this rule at all, and they can't do it reasonably. And so people like SB, person to be unnamed later, or scowled at least, they do what they call experiments. And they say they prove something. So what they're claiming they proved is that if I take a spring and I compress it with an energy to a certain level, okay, like a clock spring or anything else, that somehow, okay, when I put devices on this compressed spring or in this catapult, and then I take one that has a one mass, two mass, let's say, twice as heavy and a one mass, that somehow, okay, that the two mass will shoot it, gravity will knock it down, and it'll land here, okay, and the velocity has to be, it's a v1. So it has one velocity that gets it to here. They're arguing that, and the spring can't do that. It can't give the commensurate v2 that you would expect. That science basically would say exists, but then they'll contradict themselves. That's what the video was going before. That you'd have to have two velocity to account for the fact that you have less mass. You have the same pressure, same weight is being banged against the objects, same force, same work, same stored energy, and that somehow this one will only go 1.4 as fast, but somehow magically it'll go twice as far. So even though it's only going 1.4 as fast, that is, it's only going 0.4 faster than this velocity, it will go twice as far. Now, you're arguing if that was gravity. Well, gravity can't.
All right, so this is what Professor Lewin's going to really emphasize in these little clips, and is this contradiction. So Professor Lewin clearly argues that this would be 1/2 numbers, okay? Certain experimentalists say they've proven that it only goes 1.4 velocity, and yet it goes twice as far. So they'll concede that that this weighs half as much. This one weighing half as much will go twice as far, but somehow it'll do it with only 1.4 the velocity. That is, 0.6 of the velocity is, gone. It lost it, the momentum, and somehow it still did it. And, that's where you say, this logically makes no sense at all.
To do that, you can't use 1.4 the amount of gravity and get the same result, so that's not going to work. It doesn't make any sense. It doesn't fit with our day-to-day lives and our understanding of how things work. But they're basically saying, I give you a baseball to throw, and I give you twice as light a baseball, and somehow you can only throw it 1.4 as fast. Somehow your arm it loses 0.6. It's not.
And yet the baseball goes twice as far. So even though you only threw it with 0.4 increase in its velocity, it went twice as far. How does it do that? How does it make any sense? It doesn't make any sense. It can't be made to make sense.
That you're throwing it just half as fast. Only you have a 1 and then you add a 0.5. you're not even getting to the 0.5 addition. You're only getting 0.4. So you've lost 0.6 is their argument. A huge degrade in velocity, because they have to account for this squaring of the velocity. So, but that's all it's for, is this to satisfy this arbitrary, almost silly velocity squared. It's fun. I mean, it's just a notion, but to satisfy it, they have to do something that's just crazy. To say that the spring didn't move twice as fast. You put half the mass on it. Now it has twice as many bullies to beat up the little nerds. So there's twice as many bullies to beat up the nerds, the mass. There's twice as many bullies to act on the mass, because you've reduced the mass in half, but you haven't changed how much energy you have in here. The number of fists that are going to punch. Okay? And the idea is that somehow they're only 0.4 is effective. They can't, somehow the fists don't work anymore. And the mechanism won't apply the 2 times velocity. Which, as again, is stated to be a rule by physics that's almost as strong as any of their other rules. It's like the conservation of momentum. It's almost like Newton's third law, or equal and opposite reactions. It's like a law. But when they don't care, when they need it not to be a law, all of a sudden it just disappears as a law. And I'm arguing that's where you can see, that's where they're breaking the rules. That's where they're forcing the puzzle pieces. Okay, they're taking the piece that looks like this and they're cramming it in a hole that's perfectly round. And you're saying, why do you have all this crap on here? Well, just get rid of all that crap. Okay, this envy, this squared crap, this love for religious kooks. Religious kooks are an enemy. They're bad guys. Don't let a religious kook draw a puzzle piece for you. Okay, because they're idiots. Okay, especially scientists. You should know. As soon as a religious person says something, walk away. Okay, they're retarded. Don't get your physics that way. And then people aspiring to be heroes and wanting fame. Well, you shouldn't listen to them either, because they're dangerous. Okay, rich people. Oh, they're also dangerous. Don't let rich people do your work for you. Okay, because they have all kinds of bad motives. It's a round little piece, and it fits right in here. Just take off all this crap you don't need. Come on. Brains. Okay, so we'll play some of this. Little clips. They're just, I'm not doing this to mock Professor Lewin. I'm doing it to get to the point that there's an argument here. And there's people pretending there's no argument. No, there is an argument, that there is a real truth. There is no, we'll just pretend it's a wave and apart. No, that's a stupid solution. It's not a solution. It's a stupid mistake to pretend there aren't things like predators and prey. Okay, and it matters which one you are. It does matter. It's important. It's a huge difference.
Ratio of the velocity sloping, because you will see that v2 prime divided by v1 prime, you see it right there, equals m1 divided by m2.
So it's just basically, that's the equation. It's basically saying you really can't escape this velocity thing. If you increase the velocity in one thing, you have to increase the mass in the other thing, blah, blah, blah. The two things are related, and that is the definition of something's energy. And so, and there's no way of escaping it, in the sense that the conversion, if you reduce the mass, you have to increase the velocity, because that's the only way to make the balance balance. That's the way the scale works. The scale requires there to be more mass and less velocity on one side, or...
I guess you could say something like this is the rule where it says it always has to be purple. And we'll say that velocity is red and mass is blue. And you're always stuck. Well, see, it can't be. It has to be purple. You're always stuck making the same color. So if it's violet in, it's violet out. If it's purple in, it's purple out. It always has to be... Well, that's even the wrong way to say it, right? Yeah, because it would be the inverse color. So just never mind that I attempted to make a color analogy. But the point is that you can't have, if it has to be, you could just do this, you could just do the big V versus little v. It's always a certain amount of mass and velocity. And so you can have a lot of mass and a small v, or you can have equal mass and equal v. But it's always the same amount of weight of those two things. Never some other. It can't be something off. That's what this thing means. That's what Professor Lewin is emphasizing as a fact.
Less velocity and more mass on the other side to balance. They have to be equal for there to be where you've equitably exchanged, or if you're measuring, that they measure equal. If you slide something down the lever, okay, you're creating an artificial mass, and therefore the velocity has to change commensurate to that.
And the smallest mass will get the largest velocity.
So it's obviously an inverse relationship. So there's an explosion, the small mass goes fast, the big mass goes slow, period. And it's a tight relationship where it's equal momentum, and it has to be in the form of velocity and mass. It has to be in the form of momentum, not kinetic energy.
Larger speed. What you see in here are really speeds. don't have the information on the direction anymore.
So we don't have the information on the direction. I just threw that in because it's so silly, right? To say that somehow we forgot which way they were going. No, we still know exactly which way everything's going. We know the velocity is their direction. There was no forgetting. It didn't all of a sudden, because I wrote it on the blackboard, turn into a speed. Okay, and now I don't know where it's going. That's silly. Yeah.
And it's 488 plus or minus 1 gram. Well, that's going to be interesting, because now we really begin to test the conservation of momentum.
So that's it.
All right, so I'm probably going to keep playing this just because it's sort of, you can see part of it. See, you're only seeing part of the video, but it's enough, I think, to get the point. So maybe we'll just stick with this. Maybe I should just cut this and add this other half, because I'm probably degrading the quality a third time, but whatever. And it is sped up a little bit, so people who speed up my videos are going to be in a little bit of trouble.
Understand, he's saying the words, the conservation of momentum, and we're going to test it, and it's a real thing. It's not like a fake thing. It's a real thing. Conservation of momentum. It means you can't make momentum disappear. And you can't create free momentum. Momentum has to come from somewhere and has to go somewhere. It's not something that it lasts. It's durable. It doesn't fall into a bag somewhere and just disappear. It can only be stored somewhere.
The momentum before is 0. I will rely heavily.
Okay, so this part's kind of silly when they say, well, I'm going left and I'm going right, and that means 0. I throw something left and I throw something right, and it's 0. Well, it's 0 to me, but it's only because I can't do the, some two things hit me. They never hit me exactly the same time. You can sort of understand that. It's always going to be just an illusion that happens at the same time.
Right, so this is just the argument, right? Something hits, it's really moving it. And then the other thing is really going to move it back the other way. And you're really moving on Earth. And you're really moving in these forces. They're not canceling each other out. They're just doing their thing. And then something else does something to put you back where you were. But you're always really moving. It doesn't not move. Except electrons, technically, but I won't get into that.
What's really happening is I move this way, and then I move that way. And when I do both of those actions, I move this way, and then I move back this way. I end up back where I was. And that's all that happened. So it looks like nothing happened. Clearly something happened, okay? So if two things are hitting me, there's no such thing as they just cancel. They don't just cancel. The process happens. Just like the process of you being pushed into the earth is happening. They're not canceling. What you're feeling, on your feet, if you're standing, or on your ass if you're sitting, what you're feeling is it actually happening. You're actually moving. You can't feel it if you didn't actually impose on the earth. If you didn't push into the earth couldn't push back. So there's no nothing happening. There's no cancellation. There's an action. And one action happens and then the other action happens. And they end up canceling each other in the sense that you end up in the same space again. But there was plenty of energy. There was plenty of motion. So you're not sitting on the earth doing nothing. You are vibrating on the earth.
And afterwards is also 0. But the velocity.
Obviously, there's no zero momentum in an explosion, right? All the little bits have momentum, and they have real momentum, and they'll, kill you. So
this whole left undoes the right argument is just kind of silly, right? That only happens when the two things are coming into each other, and we say, they undid each other. But obviously, if they're going in a direction, you can understand whatever happens going right is not going to undo whatever goes left. It's not going to undo it. They're both going to do things, okay? If I shoot a bomb to the moon and I shoot a bomb to, and the Venus just happens to be exactly in the opposite direction, both the moon and Venus are going to get blown up, okay? They're not going to cancel the bombs, the missiles.
Really to say the bomb is a zero momentum event. Right? Oh, no, of course, it's not a zero momentum event. The little pieces go right through things and bore holes in them and do all kinds of stuff.
This, I erase this. V2 prime divided by V1 prime equals M1 divided by M2.
They should be saying the change in momentum is 0. That would be the thing to say, not zero momentum. Just change is 0, just like in this equation. It's just basically saying, yin yang, it has to be equal and opposite reactions. This is Newton's third law. But it doesn't mean that there's no action. It just means that the two actions negate each other as actions, and you're back where you started. You went around the circle. Going around the circle doesn't mean you didn't do anything. You did something. You went around the circle.
And so twice
in the box, okay? They don't draw that box for no reason. They draw that box to say, hey, put it in a box, okay? Draw it in a box on your piece of paper so you see it, okay? Because this is important. So just understand, this is important. It's just not some little thing you can just throw away and pretend it doesn't exist, okay? So this idea that you always have to have the same end result, the M times the V always has to equal the M times the V. The MV going in has to be the MV going out as a total.
mass will get half the speed.
So twice the mass, half the speed, clearly stated. And so this experiment's going to be different than the one I'm comparing it to. Okay, they're not exactly the same, but they're really just about, all these experiments are about transfers. Whether you're transferring from an explosion or you're transferring from one object to another object, the rules really don't change. It's the same thing. These are just transfers of energy.
Right. Well, that's something I should emphasize, just because I've been over this and over this. They don't give you a theory of the transfer of energy. They pretend that they don't know what I would argue they already know, right? Because they have analyzed bowling balls and different things. And the fact is that's what the bowling ball does. I can have the 8-pound bowling ball going 16 miles an hour, and I can roll it into an object that has a known mass, a pin. And the fact is, if it hits the pin square, right on the front, and it's going in that, in the direction, the fact is that the pin will acquire, four masses, and it will acquire the velocity, of the bowling ball. The bowling ball won't make it go 10 miles an hour. The bowling ball can make it go, really something less than 8. It'll be some little bit less than 8 miles per hour is the ideal. That's the best it can do, is give it 8 miles an hour with a 16-pound ball going. I did it the wrong way, right? This is 8 velocity and 16 pounds. So this would be 8 pounds. And, I got velocity and I got, this is 16 velocity and 8 pounds. So sorry for the confusion there. So this is the heavier ball, going slower. No, I got them upside down. Anyway, all right, so this should be the smaller ball. Well, anyway, the point would be is that the small ball going faster can give 16, as a velocity. And 16 times 4 are 64 units of momentum. That comes out of the ball. The ball has 176, let's say, units of I don't know, whatever that is. I should do that math. It's 224 or something, right? No, it's 160. No, it's 4 times 16 would be 64, right? So 8 would be 128. So 128. That 64 comes out of the 128. That's half. That's half of its momentum it lost on one pin. Where the 16-pound ball going 8 only going to lose 32 of its momentums. It's got the same number of momentum, so it still has 98 left. I mean, it didn't lose anywhere near half. It lost a quarter or whatever. So that's the difference. They're giving away their momentum in the process of moving. And you give it away to friction, you give it away to something. So I've made this argument many times, but that's what they're missing, is the idea that this isn't just some magical event that takes place. The exchange is an exchange of its momentum. It's an exchange of force. It's giving it away. When it makes something else move, it moves less. It has to give away its moving force to something else. It loses it, this gains it. It's a complete transfer. They say the word transfer, yet they don't think transfer. And that's all you have to do. There's no force of friction. I just transfer my energy to it, and I don't have it anymore. I'm going slower because I gave it to something. Period. But I guess they don't emphasize that because it makes kinetic energy theory look stupid.
And the rule is still the same. You find out what momentum is in the system and you say, where does the momentum go? You just follow the momentum. Well, in an exchange, there's only 2 sources of momentum. There's no other source. So obviously, whatever this thing has as motion is going to affect this thing with its motion. There's no secret motion. And so you have to account for it. The rule applies. And you can't pretend this one hits this one and this one does 1.4. No, it has to do 1/2.
So now you're going to see that one car will go twice as slow as the other. That's the only way that nature can conserve momentum. Nature has no choice. Nature can deal with kinetic energy one way or another, but it cannot enable momentum.
Okay, so I mean, this is a pretty overt statement that certain people, a whole group of people who hate me, they claim this is overtly not true. And instead of arguing with this guy, the guy who's saying it to hundreds of thousands of people and is called a teacher and everybody loves and adores and listens to everything they say, well, if they think this guy's a flat earther on the subject, they think he's wrong. Why aren't they doing anything to stop him? And instead they're, I don't know, doxing my family members. What the hell? Why are they, invading my personal life to tell him he's wrong? How does that make sense? Oh, that's right, does it?
will get half the speed. And so now you're going to see that one car will go twice as slow as the other. That's the only way that nature can conserve momentum.
So again, it's an important concept. The only way it can conserve momentum. So he's saying overtly to you, pretty loud. He's saying to his students, conservation of momentum is a real thing. It's not a fake thing. It's not a thing you just throw away where it's going to be. I'll just hide that. But in fact, he's going to do exactly that. Okay, so he's going to contradict himself a bit.
Nature has no choice. Nature can deal with kinetic energy one way or another, but it cannot finagle momentum.
So let's just understand, kinetic energy can be finagled because it's not real. It's the simple argument. You can finagle it because it doesn't have to follow rules because it's not real. It's a piece of the puzzle. It's been glued on by people doing shenanigans. It's been glued on by people with motivations. It's not the real puzzle piece. It has other crap stuck to it. It never belonged in the puzzle. It isn't a real thing.
So it must give the more massive car half the speed that it gives the other car. And so we're going to redo this experiment.
Okay, so
this is the other experiment. Just to point out, this is where all of a sudden the story is going to change. But clearly, there are the trolls arguing with me, say this momentum thing doesn't have to be conserved. There's no rule that you have to conserve momentum in any of these exchanges. So it's clearly against the conventional theory, and yet they don't feel any obligation to confront the conventional physicists.
I've cheated a little, and I'm playing the experiment where he doesn't do any of this crap about conservation of momentum. He doesn't do any of this stuff about half speeds or any of that crap. All of that is thrown out the window for this experiment. And he's basically proving that, oh, screw it, we don't have to worry about this conservation crap, okay? It doesn't mean anything. We can make free energy. And again, the clear implications of this experiment are there's free energy. So the number 123 is the initial speed. The mass is now twice as much, and the speed isn't 246. It's 186. So we didn't get half the speed. We got more than half the speed. A lot more. Certainly not.
Yeah, so it's 33% more, 16% more momentum. So if this was just, the first two numbers were all you looked at, and you just said we're going to make an exchange between an object that has 100 momentums and it's moving this way. The outcome of the experiment is I take twice the mass, okay, so this is 2x the mass, I hit it with the 100, and I somehow am getting 116, okay, momentums out. That is, I got an increase in the velocity beyond 1/2. So instead of the 1/2 you need to conserve momentum, I got 2/3. And by getting 2/3, I got 16% more momentum out of the experiment. So if this was a box, a magic box that just did this, it just you threw something in and I throw something out, you're going to throw in 100 bits of energy, and I'm going to give you out 100 plus 16 bits of energy out. And that's the truth of this experiment. That part of this experiment is just that. I mean, the funny part is it's going to throw another piece out this way, with another, how much momentum? It's 1/3 of this thing's momentum. So something with, 1/3 of this one's momentum is going to come out this way. So you're going to throw 100 in, you're going to get 33 cents back. Now there's a money box, right? Here's the money box. You put a dollar bill in, I give you 33 cents back this way, change, plus, okay, I give you a dollar bill plus 16 cents. So it gives you back your dollar plus 16 cents here, plus 33 cents here. I mean, you're way ahead. But obviously for a machine, for us to make a device, we're just going to talk about this way. And this way, you're clearly making energy. So I just put this box in front of this box, in front of this box. I just keep making these boxes. This dollar goes in, $1.16 goes into the next box, $1.50 comes out of the next box, $1.70, $2.25 comes out of the next box. I just keep increasing how much money I'm making. It's a free energy formula. It's a free energy experiment right in front of your face. Right there is, he's saying free energy because it's not 1/2 the velocity. As he said, it has to be to conserve momentum. He didn't conserve momentum. He's made more momentum in the direction, clearly, overtly, made free energy. I mean, and people claim they can't understand why this is a problem.
1.4 either. I mean, we're certainly not at 1.4 speed. So, you know, what gives? You know, why the double standard? Why all of a sudden is momentum allowed to not be conserved? And it's momentum in one direction. Obviously, they're playing a game because something went this way. They're pretending that undoes the motion this way. So even though we have way too much momentum going that way, we'll pretend that this one undoes it, and so therefore it's canceled. But it's real energy. It's real vibrations. You know, you can't just sit there and say, I put in this much. And, well, I got this much this way, and I got that much that way. But that way cancels this way, so I really didn't have any extra energy. Even though it really went, the larger swings. And it doesn't make any sense for you to say, well, I'm just doing the minus math, and the minus math pretends there was no energy. It was real energy. It's a real swing too much this way. The pendulum's moving too much this way. The fact that it goes back that way doesn't undo that it went too far this way.
Was indeed extremely close to one mass is 241, plus or minus 1 gram, and the other mass that I have is 482, plus or minus 1 gram. And I have two of these. In my first experiment, I will use these two here.
So just clarifying that this is he's just doubling the mass and expecting the half the velocity in the other experiment.
This, I bounce one card into another one which is twice the mass. So the velocity, which I don't know what it is.
So he starts with an unknown velocity, which is fine, and then he's going to say 2/3. When he just, you know, in the first half of what I just played, he just made an emphasis. You can't finagle momentum. The speed's you're going to hit something twice as massive. It has to go half as fast. It can't go 2/3 as fast. It has to go half as fast. It can't go 10 times faster. It can't go any kind of faster.
So just to establish, again, it's essentially the same experiment in the sense the transfer is just going to be between, instead of having an explosion, a neutral device producing the energy, you're just making a transfer. The same rules apply, the same rule that momentum has to be conserved. And so if you're transferring from a one mass object to a two mass object, it's the same thing as having an explosion between the two. And what you're really just saying is yeah, obviously to conserve momentum, I have to get half the velocity. I can't get 2/3 the velocity in the twice as massive object without gaining momentum, without creating new energy from no source.
If it's going any kind of faster than half as fast, you are now creating free energy in that direction. You've got more momentum moving in that direction. So I'm just saying, can anyone provide any argument, any kind of reasoning, that if I take something in and I make more momentum coming out in a direction, that isn't some kind of energy that can be captured? That some idiot, couldn't do experiments where he could create a machine that collects all of that extra momentum? Because it's a simple process. All you did was bang a half mass object into the, you banged a one mass object into a two mass object and you got more momentum out.
And so you just keep increasing it. 2, 4, 8, 16. You just keep doubling the mass increase, and the momentum will just keep increasing by 16% each time, and it's compound interest. You're getting interest on your interest. You're increasing your 16% by multiplying it by 16% again, adding 16% to your 16% that you gained. Your interest is now gaining interest. So clearly it's a perpetual motion machine and a perpetual energy machine.
That's the end. So all you have to do is bang it into another more massive object. You get more energy out. More momentum, more momentum, more momentum. Momentum is energy. It's never not energy. I mean, even if you believe in kinetic energy.
Again, if we could just extend his air track theoretically very long, and we could suspend any weight object on the air track, the clear implication is that you could just keep increasing the mass that the thing bangs into. You just keep banging it into a heavier and heavier and heavier object, and you keep increasing the momentum.
You must concede that momentum is always energy. I mean, it's always more momentum is always more energy. You can't have more momentum and less energy.
Momentum, again, is weight. Gravity gives you weight on Earth. It's your momentum. It's weight. It's your energy. It's your weight. It's not your mass. It's your weight. If I make you go twice as fast, I've doubled your weight. It's your weight that gets doubled. You hit it twice as hard. Okay? 4 times. 4 times as hard.
And now, what are we going to get? So mass M1 is half the mass of M2. So this is 1, and this is...
So you can't see the formula, but the formula is the bastardization of derivatives of mv and then made equal to 1/2 mv squared. So they take a rational derivative of the simple concept that mass is related to velocity in not a squared half ray, and then they compare it to a derivative of that, and then they take those two ingredients and make their Frankenstein equation, an equation that is half good, half rational, and half bullshit, and they get rational bullshit.
Let's understand, this is the equation, and how they make this equation, they did derivatives of the two concepts. So they took wave, and then they took particle, and they blended the two things into each other and made an equation. This is what this is in the kinetic energy realm, or the energy realm. It's the same idea. They took momentum in a formula, an idea of it, a redescription of it, and kinetic energy in a redescription of it, and then they combined those two to create a new universe where that puzzle piece makes sense. They made a Frankenstein out of the two things. The two things were different, and they forced the two things.
They just forced the round peg. Okay, mv squared is, let's say, the round peg with fake crap put on it. And now they're creating a new hole to put the malformed peg into. So they're just reforming reality, okay, to say that the bastardization of these two things creates some sort of new shape that is the actual shape of reality. When no, it's a round hole, and you just should stay with the round peg.
To be the same thing and equal. So they took two things that were both distorted and made a new distortion. So that's where this comes from.
The 2, and this is 3. 1 minus 2 is minus 1, divided by 3 is minus 1/3. So number 1 comes back. No surprise.
So it's a huge surprise, really, if you're going to be pushing more momentum forward, that you get even more, you get some more stuff coming back. I mean, that's kind of free. So you went in with something going this way. You're going to get something back this way, called change, so to speak. You're getting a third coming back this way, which is like, well, if I'm getting more momentum that way, how can I get any momentum this way? If I'm getting some this way, how did it go that way also? It can't go both ways, right? Logically. All right, and the key to this whole thing is also part of the strangeness, right? Because they have the idea that these are rules for elastic collisions. That is, collisions where pieces don't fly off and the thing isn't mushable. So if the idea is that you have a clean transfer. And so they talk in those terms, but the fact is these are steel objects. They're considered elastic, and yet you had to put springs on them. So now we're back to springs as storage devices, and how do they exactly work in terms of if the spring is moving, into the compression, or whether you're compressing the spring. Is there some way it makes a difference? Somehow the spring is allowing you, okay, to use energy twice in a sense. You're able to push the object, so that's how you got the 2/3 going that way, and you're also getting a third back this way from the spring. So somehow you use the energy twice, which is sort of against the rules.
If you bounce a lighter object off a more massive object, no surprise that it bounces back. So it's minus 1.
But in elastic collisions, it's sort of a surprise, because what the expectation is that you have a clean conversion. That, if you hit it with a little thing going fast, the big thing goes away slow. Well, the truth is the big thing doesn't absorb the energy, then it bounces back. But it only bounces back proportional to how much the big thing doesn't move. If the big thing does move, it doesn't bounce back. So it's just about how much energy you give the big thing. So if you only give it half your energy, then you still have half your energy, you bounce back with half your energy. But the rule still has to be follow the momentum.
All right, so the idea is the springs are adding a new feature into this, and I would argue that the springs are responsible for the thing going back 1/3, because you're clearly compressing the springs, the motion's going into the other object, and then the springs expand, and that's creating the 1/3 backwards, and it's creating the 1/3 in velocity the other way, okay? But it's not 1/3 over the 1/2. I mean, it's the 1/3 short of 2/3, right? So instead of all the momentum going, 1/3 went this way and 1/3 went that way from the springs. And this was supposed to be 1/2 the momentum from just the objects themselves. So again, why take something and say this is an elastic collision when it's all by itself with no spring? We'll call these things elastic. Both these cars are elastic by definition because they're just metal. They're elastic. They don't break, pieces don't fly off, they don't bend, they don't deform. So they're elastic. How come we're putting springs on it and then just saying they're elastic again? I mean, it's clearly there's something way missing, okay? Their physics is way undercooked to have a word elastic where you create two completely different experimental results merely by putting a spring on. The springs are essential to this experiment working. It won't work If he doesn't put the springs on and he does the experiment, it won't work. And he knows it. That's why the springs are on it.
Where does the energy go? And it can't go to both. You can't bounce back 100% and move the object 100%. You can't have 100% momentum went this way, that way. 100% of the momentum went that way, and 100% went that way. You can't make 200%. You can't make 110%. You can't make 135%. You can only make 100%. You made that rule clear, and you do it in a box. There's only 100% momentum. There's no, I made 90, I made 110. There's only 100%.
And when we look here, we have 2 times 1 divided by 1 plus 2 is 3. That is plus 2/3. So number 1 will come back with a speed 1/3, which of course, since this is sign sensitive, we get 1/3 v1, and this one is plus 2/3 v1.
So that's v2. That's the object is twice as massive. So the rule is half the velocity. So it's really, this is all the experiment is. It's an object going in, hits another bigger object. Somehow, this other object, doesn't have to obey the conservation of momentum, and it's going to leave with 2/3 instead of the 1/2 he explicitly said you can't finagle with. You can fidget with, or whatever the word he used, right? You can finagle. I think that's what he said. But you can't do it. Kinetic energy. But you can't finagle. Nature can't finagle momentum. Momentum's a real thing. It has to do with the little bits of the mass, the little objects of matter, and your ability to move those at velocity. And there's no theory, that permits 2/3.
There's just so much energy in your soldiers, right? I mean, your soldiers do work, they lose their energy. You give your energy to the world. I mean, that's the way it works. And that's friction, and that's all the other ways you exchange it. The exchanges never are, I gave it away and then I used it again. There's only so much money you have when you have energy, and you give it away. And you can't keep it and give it away. You can't do both.
There's no logic that permits it, and you can't defend it. You can't defend conservation of momentum and say that makes any sense. Because an explosion can't do that. No other mechanism that creates velocity can do that. Can take the 100 that went in and make 125 come out. And that's the implications of the 2/3. Is you're making, it's too much velocity for the mass. You've given it more momentum. The 2/3, twice the mass, is more momentum.
You only had so many people on your side of the pull of, the tug of war, the rope. And yet somehow you magically just created another 16 guys to pull. How do you do that? Where do you get them from? Where did they come from? The two-mass object leaving has more energy. Just a fact. It has more stuff going this way. How did it get more stuff going that way? In the sense of either more soldiers or more walking steps. Those are the two things. How do you can't have more of it. You only had so much mass and velocity, and you can only have so much coming out, and you can't make 16% more and say I got it from nowhere. That's free energy. It's a free energy statement right there in front of you. It's overtly contradicting his own theory, and he has no theory to defend the contradiction.
And then the one, velocity and one mass had going in. The one mass and one velocity going in can't make that extra momentum out of nothing.
V1, and this one is plus 2/3 V1. Here, the forward speed is 2/3, so it will go slower.
Right, but not slow enough, not one.
Yeah, not slow enough. So I just wanted to emphasize that. Yeah, it's going slower, but not nearly slow enough to conserve momentum. It's way too fast for what pushed it. There's not enough mass and velocity pushing to create that much mass and velocity. There's no way to make it make sense. It's a clear violation of conservation of momentum.
Half. So he overtly, let's just understand, the principle is it has to be 1/2. He said it. It has to be 1/2. And now all of a sudden it doesn't have to be 1/2 anymore. Hell with it. We have 100 momentums going in. We can have 125 momentums coming out. It's okay. Don't worry about it. Well, it's actually 116. 16% more energy. The difference between 2/3 of the velocity and 1/2 the velocity will be 16% of the momentum. So it's gained 16% in its momentum this way. And there's absolutely no reasoning that defends the creation of that free energy. You people really should be able to follow along. I mean, I have made so many videos, and I have to just redo this over and over again.
We have multiplied this time by 2/3, then I should be able to compare it with T1. And all these times, the V4 is 0. I bring the y momentum afterwards is also 0. But the velocities, oh, I erase this.
So I'm just going back to what he said, back to the this is the conservation of momentum. So here he's teaching the conservation of momentum, and the other experiment he's teaching, I don't know what the hell he's teaching, because he's teaching that free energy is right there to be grabbed, that you can create free momentum, and that we all should be making our free momentum device. We all should have no electric bill and no gas bill and no fuel bill for the car or anything. I mean, everything should just be free, because we should have a little perpetual motion machine that actually makes more energy all day long. It just keeps making 16% more momentum over and over and over again. That's what science says.
So that's a clear distinction. 1 minute it's a law, it belongs in a box, it's important, it always happens, there's conservation of momentum, it's an important theory, important concept. Next minute, it really wasn't next day, next week, a month later, we won't even talk about that because I need to do this 2/3 thing to make this other crap make sense. Crap that really doesn't make sense, right? Because again, we have no evidence that to go 60 miles an hour you need to use 4 times as much fuel. And we have no evidence that when a rocket is going in through space that somehow the fuel it uses 10 minutes later, you know, when it's going faster, that the fuel has more energy in it and it can make even more speed because somehow the fuel is so much more important when you're already going fast. That somehow it just makes the fuel more excited and more helpful. We don't have any evidence of that. We don't have any evidence that the fuel is less potent taking off. You know, we don't have any evidence for the consequences of their violation of the theory. So when he violates what's in that box, it just creates paradoxes. It just creates problems.
V2 prime divided by V1 prime.
I mean, he's famous for saying physics works. So this works. It can only go 1/2 as fast, but it can go 2/3 as fast. Because physics works.
Prime equals n1 divided by n2. And so twice the mass will get half the speed. And so now you're going to see that, well, I erase this.
Just keep watching him make the box.
Equals n1 divided by n2. And so twice the mass will get half the speed. And so twice the mass will get half the speed. And so now you're going to see that one car will go twice as slow as the other. That's the only way that nature can conserve momentum. Nature has no choice. Nature can deal with kinetic energy one way or another. But it cannot enable momentum.
Yeah, sorry about the distortion in the sound. But it's really so important. Okay, you hear him saying it. It can't finagle momentum. Okay, yeah, kinetic energy, okay. We sort of made that up. It's bullshit. We can fuck with it. But clearly, you know, he can't even stay true to that concept because this stupid formula has invaded, and diseased their physics. It's diseased it and forced them to do things that are just completely nonsensical. He did a free energy experiment. Nobody recognized it as that, but they should have announced it in the newspaper. Professor Lewin's going to demonstrate free energy. Because that's what he did.
It must give the more massive car half the speed than it gives the other car.
Must.
So it's clearly stated it must, and therefore, no, that's a must, because when I don't need it, want to, my equation says otherwise, I just change the rule and we'll just forget about that whole idea. The concept is meaningless. And for no good reason, I'll just change the concept. The conservation of momentum's momentum. You know, who cares? And, you know, it just doesn't make any sense. So there's so many ways to look at this and just say, why are the springs on the carts? They're obviously doing something. They're doing something more than just making it a pure kinetic, a pure elastic collision. But do we think we can do this in real world? Can we make things can we get more momentum out of the system? And I would argue, well, we all should know you can't do that. So there's a real problem here, because you have to say, not only is the theory incredible, that we've just been told, not is only full of a contradiction, an overt contradiction. Conservation of momentum, sacred, important, put in a box. Conservation of momentum, forget about it, we don't need it, in the next minute. But we have an actual experiment. Okay, we're told, look, I just did it. I just made free energy. It was a free energy experiment. And your only choice is to say, do you understand logically that free energy really can't be possible? That the universe would have already been using it, right? If there was a way to get free energy, we wouldn't have to eat, okay? Because evolution would already take advantage of it. Evolution would have already found this trick where I just bang things into each other and I get free momentum out of it. I get extra energy. It would have already found perpetual motion, so to speak.
You could understand that in some way or another, okay, evolution would have jumped on, all I have to do is put springs on light objects and bang them into heavy objects and I can make free energy. So it would have already made a little mechanism inside of us that just creates the little perpetual motion clock that just creates the perpetual motion device, all right, that keeps the energy just increasing and increasing and increasing, and it just pulls it off. So it just keeps the perpetual motion, and it just takes all the extra energy that it keeps creating. It keeps creating. It keeps creating more and more momentum, more and more mass and velocity. I mean, more illusionary mass through the process of velocity. More weight. It keeps making the heavy thing heavier and heavier and heavier by giving it more velocity.
If it was available for us to exploit, it would have already been exploited by, a billion years of evolution, chemical evolution. And it hasn't. So that's good reason. That's just to reckon, oh yeah, that's got to be crap somehow. And if it's crap, it means, But again, I can't cast the aspersion unless somebody has, maybe somebody has an explanation. But I don't see what the possibility is. You either have to accept that this is really bad science and that experiment has to be rigged because it's basically a free energy experiment, or there is free energy and somehow evolution's lame and it didn't take advantage of it, and somehow the hundreds of thousands, if not millions, of scientists who have tried to find free energy who haven't been able to do it were really incompetent. Because
yeah, I mean, it really is a dramatic statement, right? So, I mean, it's really hard to believe that free energy was right here. He even described it in a video, even did the experiment, and they still didn't figure it out. I mean, he basically flew the plane in the classroom and then is saying, why hasn't somebody invented flight? You just did it. We already did it. We're done. So why don't we take advantage of it? Why don't we start flying around? Well, why don't we start making our free energy machines?
Shit. It's been right there in front of us all of this time. You just bang a light thing into a heavy thing, an elastic thing. Okay, put a spring on it. It helps. Maybe a tree branch. You just tie a tree branch to it to make it springy. So you take a light thing and tie a branch on it, and take a heavy thing and tie a branch on it, and you just bang the light thing into the heavy thing, and bingo, you're making energy. You're not using energy. You're making energy. Because you just do a bunch of them in a row.
And even if you made it really inefficient, so it used up that 16% increase with each thing, and it just used up 15%, let's say, and so all you had was perpetual motion, you'd still have a battery-less clock. All of this stuff could have been invented an awful long time ago if they just took advantage of just putting something springy on something, and banging light things into heavy things.
Make a circle out of it, and the circle will just keep going around and around and around. All right, so I've done my job again. I'm attempting to reason with you, to explain that there's Houston, there's a problem. Okay, this is not, there's a real inconsistency here. He just described a puzzle piece that's this, and now he's using it, and it's a square. I mean, square pegging, round holes all over the place here, and there's got to be, that just can't be the way it's supposed to.
You can't have a complete rule change and just subtly not even talk about it. Not even to say, like, oh yeah, I'm writing 2/3. I mean, I am breaking conservation of momentum in this direction, because I'm pretending, because I shot a bullet that way, I undid the bullet going this way. Yeah, I know that doesn't make any sense. How do you undo the bullet going this way by shooting a bullet that way? That doesn't really make any sense. Yeah, I know. But we're just going to pretend. That's how the universe works.
To work. You don't change the rules in the middle of the writing of the rule book. No, not good enough. All right, I think this is. I really can't imagine that I could present this argument to you in any form better.
So I wish this video didn't get broken because, yeah, I thought I did a good job. And this is going to be less good because it's not as visually accurate and all the, it's distorted and the sound isn't going to be great. So sorry about that. But I just couldn't imagine redoing the video. I should have probably imagined doing it and did it, but I didn't. So you got this instead. It's about the same amount of time, I think. Let's see. Yeah, well, an extra 12 minutes.
Than this. Like, I'm going to do it differently than this. I mean, you really should be able to understand how this isn't something to ignore and pretend it's not a real problem. It's a real problem. It's not a fake problem. It's not something I made up. It's not just blah, blah, blah. It's a real contradiction.
You can't have momentum and kinetic energy formula. You can't have these two formulations coexist and say everything's okay. Because it really isn't okay. It really is screwed up, and one causes the universe. Forcing them together creates this paradoxes of the fact that you're going to have formulations where you're making free kinetic energy or formulations where you're making free momentum, and you can't evade those conflicts. It doesn't work. You have to choose a side. One of them right, one of them wrong, or both of them wrong. But you can't sit there and pretend it works as an idea that they're both real things, because they're not.
Explain it. Or agree that there's a problem, and somebody ought to look into it. We ought to investigate how this is possible. People who are competent at doing experiments ought to do experiments and resolve this conflict. Anyway, talking to the internet. Probably no point. Anyway, till the next time and such.
Probably no point, I said. Yeah, it really is. I really just didn't think it was impossible to reason with the human race, but it looks like it's impossible because the smart people are unreasonable, and that's the part I just didn't anticipate.
Yep. Like I said, all I can do is I can just do my half. I make a reasoned argument. Can you make a reasoned reply?
The simple answer is no. Okay, to that question, they will not make a reasoned reply. There'll be no reasoned reply. The AB sciences of the world, all these, fatheads, will not reasonably reply.
This has been
Yeah, well,
DraftScience video presentation and such. Yeah. Until the next time.
So anyway, it was a good video, but shit happens, as they say. I say it more often than I would like, but it's nothing you can you can't do everything well, right? Alright, so yeah, I do physics pretty good, but okay, I don't do video production very well. So anyway, till the next time, and such, and so forth, and whatnot. Blah, blah. This has been a DraftScience video presentation. Pretty much.